So our next speaker, as I said, is Roland Logé from EPFL in Switzerland. Roland has done a lot of work in solid state metallurgy and material science. And since the middle of the last decade, he has been working a lot in metal manufacturing, leading some consortiums in Switzerland. So today he's going to talk to us about porosities and cracks in powder bed fusion. Roland, please, the floor.
Thank you. Thank you very much, Manas. So yes, so first of all, I would like to acknowledge the number of people who contributed to the results I will be presenting today. Several of them are from my lab at EPFL, but also some like Stephen and Elena are from the Paul Scherrer Institute, and then Kilian Watzmer and Christian Lennenbach from EMPA. So I'll be talking about porosities and cracks in laser powder bed fusion. And here is the outline. So first, I'll talk a little bit about the defects of interest and how we usually define processing window in laser powder bed fusion. Then I will go on a particular type of processing map, which uses the concept of normalized enthalpy, and show that actually this is quite convenient if you want, for example, to have an accelerated search of optimum processing parameters. For example, if you identify that for one material, how you can jump quite quickly to another material, remaining on the same machine. And then now, since we talk about defects, I will show some of our results on the monitoring of defects by acoustic emission. This is in a collaboration with EMPA, Kilian Watzmer in particular. And at the same time, not only we have in mind to do monitoring of defects, once we recognize those defects, we would like to locate and maybe repair those defects. And I will show one example of a strategy using laser shock pinning which allows actually to heal cracks in the nickel-based alloy that actually we have seen already in Stephen's presentation. So first of all, a few words about the process. I mean, I don't need to introduce the process, it has been presented already. Just I want to emphasize the very high heating and cooling rates, which lead to some kind of a special metallurgy, the type of alloy that are suitable for these type of fabrication, difficulties in dealing with time and spatial scales, which cover a wide range in modeling, very special thermomechanical treatments undergone by a material, and also we have seen how sometimes difficult it is to manage characterization of good quality in these materials. When talking about defects, you have the well-known porosities. That's an example. I will come back to that, or the gold alloys. We work a little bit on those. And these are highly reflective materials, well known to be difficult to process. You also have the possibility of having cracking. We have talked about it already. These cracks can be major cracks, like macro cracking. In this case here, it's a tool steel. But we can also have smaller scale cracks, like the ones we discussed on the nickel-based super alloy CM247LC. So those are widespread, and this makes this alloy very difficult to process by additive manufacturing at the moment. Porosities, well, I will distinguish mainly those two type of porosities. Either you are typically at too low laser energy, then you have this lack of fusion that Philip also described in details on the tomography images that we saw. And also, when you are typically at too high energy, then you can create the so-called keyholes. Usually, you have these very deep then melt pools, and associated with those, sometimes you create these porosities, which can be quite big. So you want to avoid both types of porosities, and so people often use these processing maps where you have the scanning velocity on one side, the power of the laser on the other side. And in this is the high energy range for the keyhole mode. The lack of fusion is a low energy range, and you want to be here in the intermediate so-called conduction mode. Now, many people then, instead of using two parameters here, try to put that together in the energy density, which is basically looking at where more or less the energy from the laser is distributed. And you kind of define a little prismatic zone here where you assume that most of the energy is distributed. And that it actually takes the hatching distance, so the distance between two track lines, and the layer thickness. So it's a crude approximation, but it can be a first step to describe what happens. And then an important parameter here is the absorptivity of the material on the surface. Basically, you have only one part of the energy which is being absorbed by the material. The rest is being reflected. I will come back to that actually when talking about the normalized enthalpy approach. So looking closer, I mean, we can define a little better what happens in terms of laser material interaction. You have typically a liquid zone here, a melt pool. And then when we talk about laser absorptivity, well, that's not the same if the laser comes here on the liquid, where you have surface absorptivity, or if a part of the laser beam also comes in the powder, because then you have multiple reflections and certain penetration depths of the laser in the powder bed. And then we can define a powder layer absorptivity, and I will describe that afterwards. You have also heat transfer between the different zones, between the liquid and the already solidified material, but also between the liquid and the powder here. That can be described by a thermal diffusivity. But again, yeah, we have this issue here that we need to resolve. Very often when people describe energy density in literature, they use some kind of an effective absorptivity here. But if we think about it, it's just a two-phase problem where we have a volume fraction of one and of the other, and somehow most of the time people use an effective average value. Also, we have large temperature gradients here because the zone is quite small, and so very large cooling rates and residual stresses. As you know, these residual stresses come from solidification shrinkage and combined with the large temperature gradients that also have an influence in the solid state when we keep cooling down. So typically you have tensile zones here near the top surface and compressive zones when you go away from the external surface. Now, I just want to mention two papers that I find interesting, where in the melt pool here, they measured here in 2018 the temperature field in the melt pool and showed how variable this temperature is, and also the temperature gradient. So that means that the solidification microstructure is actually different at different zones. And that means they are more or less prone to defects in different locations. Also, another, oops, yes. I guess my screen is a little frozen. Oh, okay, suddenly it comes back. So another paper which is quite interesting is now looking at the cooling rate in the solid state, and that's the example here of a Ti-6-4 that Stephen discussed already, where the cooling rate going from the high temperature beta phase to the alpha phase will depend typically on the laser energy. So you have the laser power here, and you can see that the larger the power being used, the larger the melt pool size, and then the slower the cooling rate. So again, this will influence microstructures, residual stresses, and then the tendency of forming defects. Okay, so now these residual stresses, they can produce shape distortions, as well known, and you can visualize that typically in parts. This is here base plate, which is being bent actually because of the presence of these residual stresses. They can cause cracking also during processing, and as discussed by Philippe just before, they have consequences on the fatigue life of the material. Now, after this introduction, I just want to now introduce the type of processing map that we like to use. They are based on the normalized enthalpy concept, which itself was actually introduced in the welding community. So we do not invent anything here. So you define first what is called the enthalpy, which is somehow an energy balance, the amount of energy that is being absorbed by the material. So you have the laser input, and then you have some heat dissipation, which comes here with the diffusivity of the material. You have the spot size here, and again, the absorptivity of the material at the surface. Typically, then we normalize this quantity of increase in enthalpy of the material by the melting enthalpy. And so that's convenient because you want this ratio to be at least 1, such that you melt the material. So you start here by values of 1, and then you keep increasing. And you plot vertically here the melt pool depths that you can measure. And again, you normalize it by the spot size of the laser. What you find is that at lower energy, not a surprise, you see lack of fusion. And at higher energies here, you see a change of slope, which is the consequence that you have keyhole defects. And as we know, a slight increase in energy in such a case increases very much the depth of the melt pool. That's why you have 2 different slopes here. And the sweet spot is actually at the intermediate zone that we call the conduction mode. So basically that would be here the processing window that you're looking for. So it's a 1D defect process window because we usually just use one quantity here in the same way that some people use the energy density. Now, if we look, and in the literature, it was quite well known, it was well shown that if you use the energy density in 2 different cases, you might have very different melt pools, whereas if you use instead similar normalized enthalpies, you usually, if you change the power and velocity, you remain in the same processing mode. So we can rewrite actually this normalized enthalpy by the product of 2 terms. One is material parameter, material related term, basically, right? You have material parameters here, including the diffusivity, specific heat, latent heat of melting, and the density. You have another term here, which is process related, where you have the power, the velocity scan, and also the spot size. And then on top of it, you still have this absorptivity value that we discussed earlier. So now let's see with this type of processing map, how we can benefit from those maps for an accelerated search of optimum processing parameters. The reason is that if you look at the full list of parameters on which you want to play to optimize the processing, is sometimes very long, it can be very expensive. Here I illustrate again the case of a gold alloy, where you see in blue here the little porosities. It's actually quite difficult to measure that in tomography. So in this case, it was done by neutron tomography at PSI together with Pavel here. But if you even look at a more standard material like stainless steel, you will see that the range of so-called optimal processing conditions is very large. Sometimes the spot size is not even mentioned. They are machine dependent. And well, if you analyze that further, you still find that the normalized enthalpy seems to be a better, less varying than the energy density among the different values given. Okay, that means you cannot really rely on literature to find optimal conditions most of the time. Let's imagine that these maps are quite universal in the sense that these optimum values of normalized enthalpies are the same regardless of the material. So let's keep that idea and see, well, in that case, you would have some kind of an optimal value here, which would be the same for material B or for material A. So if you have identified optimal values for B, well, you just get immediately by taking the ratio of the two normalized enthalpies, which should be equal to 1, basically. That's how you get immediately the optimal values for the new material. Now, of course, there is these quantities here that you need to identify. The M values are material parameters. Most of them are okay, but then what about the diffusivity? Because you have 3 different states of the material here. You have powders, you have liquids, and you have bulk solids. And same for the absorptivity, actually. You have on the surface, you have either the powder or the liquid interacting with the laser. Oh, okay, I forgot to mention another way of using these processing maps would be to say, no, I keep the same material, but I change the spot size. If I do that, well, as long as the process-related parameter remains constant, I can adjust the 2 other parameters. So that's 2 ways of using it. Now, what we can say about the last comment that I made on the diffusivity here and the absorptivity there is that obviously the solid, the diffusivity in the solid here is much larger than what we have in the powder. And also, usually, if you integrate the total absorption here in the powder bed, it's usually larger than what you have here on the surface of the liquid. Now, from this, you can make a number of assumptions, but we also wanted to do detailed finite element calculations. So we have an in-house code where we do describe the 3 different phases, the powder, the liquid, and the bulk solid. And then this is a 2D view, but these are 3D calculations. You refine the mesh close, the spot size, and in different calculations, what we found is that if you use a uniform bulk solid diffusivity in the simulations, actually the melt pool size varies by less than 10%. So considering the maps that I've shown before where we use this melt pool size, it's a reasonable approximation to consider just 1 single parameter for the diffusivity. So that's one thing. Now, oh, yes, it's a bit slow. Now, if we look at more detailed finite element simulations, where you describe the presence of the liquid, the solid, and the powder, that's the consequence of the calculation here. And also, you approximate the laser beam shape as a Gaussian, as most of the people do. Then you can look at what happens at the interaction with either the powder or the liquid. So at the powder level, you can actually find penetration depths, which you can measure experimentally. We have done that using a spectrophotometer. And basically, the amount of energy that is being absorbed there is, well, the incoming intensity, you subtract the reflected one, but also you remove the transmitted one here. And that defines it's not anymore a surface quantity, but it's a bulk value, giving that what we call the layer absorptivity. And that is what we want to consider in our processing maps, actually, as opposed to the standard approach, which is just subtracting the reflected light here. Then you have defined another absorptivity, which would just be based on what happens at the surface. So if you do that, then you correctly reflect the fact that everything happens on the surface on the liquid part of it, but for the part of the beam that goes into interaction with the powder, you have a penetration depth. Now, these simulations are useful because then you can check how much this average absorptivity that we can compute, taking into account both phases, relates to the powder layer absorptivity that we just defined. And we take the ratio of those two, and if you remain in the conduction mode, so before reaching the keyhole mode, what we observe is actually that this ratio is more or less material insensitive. And you can see that we selected three very different types of materials, stainless steel, red gold, and bronze. In particular, their reflectivity is very different. Their conductivity as well. That means that's very convenient, because then if you're looking to at the ratio of the absorptivities of two different materials, you can approximate that by the ratio of these powder layer absorptivities, which can be measured. The liquid one is much more difficult to measure, actually. And also, you don't need to know the volume fraction of each of those two phases. So that means then that you can come back to what I would call then a translation rule, and simply use it with the ratio here of the powder layer absorptivities and using the solid bulk diffusivities here in the material related parameter. That means that, coming back to the initial question, the optimal normalized enthalpy is indeed a unique reference that can be used for different alloys, at least for the three different ones that we have looked at. Actually, since then, we have worked on other alloys, and they keeps working quite well. So it's an example here where we optimize the processing of bronze. And again, the sweet spot is at the intersection of those two lines here. And actually, if you now go to red gold, you can see that we started from the same point, and one or two iterations where it's enough to get really the optimal density very close to the other one. And in the same way for stainless steel, where in here, not only we change the material, but we also change the spot size, which also enters into the equations. And so if you summarize, we had each time a very high density for the three of them, and for gold, it's actually the best reported one. So that seems to be working well. Now, of course, these are statistical regimes. So with these process maps, good, you are in the so-called conduction mode. That doesn't mean you don't create defects, because many of them are stochastic in nature. You cannot prevent defects from happening. But the idea is then to find some kind of efficient monitoring methods to see these defects when they form. A lot of people have been looking at thermal measurements, which are usually just on the surface of the material when it is being processed, which is a limitation. That's not the case for acoustic emission. So we have been collaborating now for a few years with Kilian Wasmer at EMPA, and the idea is to just introduce a microphone in the material and then measure, record the acoustic signals. And then with a machine learning analysis, you can use different types of algorithm, try to distinguish the acoustic footprint behind the formation of defects. So we can, on purpose, actually, using the processing maps I just introduced before, go in the keyhole mode, like a fusion mode and conduction mode. Here's the setup in our machine. You have actually a microphone which is put there, and you can see here, this is the base plate. This is an in-house machine, and that's the gas flow system here. That is the work of Rita, Dries Sidaoudi here, and PhD work together with EMPA. And so on purpose for the three materials here, stainless steel, bronze, and this time Inconel 718, we go in the three different modes on purpose, and we record the acoustic signals. And then it's called supervised learning, in the sense that we tell the algorithm, and we tried 4 different ones, which are listed here: logistic regression, random forest, support vector machine, and convolution neural network. I'm not an expert in those algorithms. This is really something that is developed at EMPA. But the important message here is that for those 4 different algorithms, if we have trained the system to recognize the acoustic emission in different processing regimes, once we then use new recordings, not telling this, what kind of regime it should be, then you can see that at around 90% in average, regardless of the type of algorithm, it can recognize whether it is in lack of fusion regime, keyhole, or conduction mode. So that's a very good classification accuracy. But you can actually do even better. So here you do that on separate materials. The next step is that you combine the material data sets, and then you test for each material and regime, but not saying which material it is. And actually it's still there, actually, as long as the material is in the database, then you can recognize in which regime you are, again, with a very good classification accuracy. So that's very encouraging because if you want, for example, combine different materials in multi-material printing, as long as each of the materials you're using are in the database, you can tell which kind of defects you have. And actually, you can do even better. You can say which material has been actually subjected to a given type of porosity. Now, the next step is obviously localizing these defects after having said that they are present. So that we're working on that. It starts working well, but it's ongoing work, I would say. But so there is a certain resolution by which you could say these are tomographic images here, and then you actually, if you have the same baseline here, recording the time and making the connection between time and space as the laser moves, you can connect these two information. And if you have a reasonable resolution here, the idea is then to come back with the laser and then remove these defects. So we have different strategies in mind. One way is just to do simple remelting operations, but we can also use other methods. And I just want to finish my presentation, the last 5–10 minutes, talk about a hybrid process that we have been developing also for the last few years, which is called 3D laser shock peening, which allows to change the residual stress state in the material as we built it by laser powder bed fusion. So if you change the residual stress in the material, you either prevent crack from forming during or after processing, but also I will show you how we can also repair existing cracks. So just a few words. It's a well-known surface treatment, laser shock peening. That's not new. Huh? You have a laser beam coming on the surface. Usually you use a so-called ablative layer here on top, which is absorbing most of the laser energy. Can be, for example, an aluminum foil or carbon tape. Then, because of the high energy pulse here, these are typically nanosecond lasers. You have high energy pulses that are being absorbed in a short amount of time that creates a plasma, and the fast expansion of this plasma creates a shock wave which goes into the material, and the shock wave itself creates plasticity, typically over a depth of something like 1 millimeter. Depends on the material, of course, but that's the order of magnitude. Now, the shock wave could go upwards as well, but that's why you use a so-called confining medium. Here, oops, it seems again to be slow here. The confining medium that people use usually is water. Okay. I am again stuck in the...
Maybe you can stop the sharing and reshare.
Okay, yes. Oh, okay, now it's back. You know, it is sometimes it takes a number of seconds. Okay, so the confining medium here is typically water. It's transparent. The idea is that it's transparent to the laser, but at the same time, it prevents the shock waves to go upwards. So that means the maximum is going down into the material. That's what we want. Now, in doing that, it's known that you create plasticity, and the plasticity itself creates compressive stresses. So if you measure the stresses here, that's near the top surface, and you go deeper and deeper into the material, you can see that initially you have something that is tensile, but if you apply these shock peenings once or twice or 4 times, you are more and more compressive in the near surface region. Okay, so that is very good, because then it has a well-known improved fatigue life behavior if you surface treat the material like that. In the lab, you can use this type of setup where you use water as a confining medium. But we wanted to go further, and why not using that repeatedly during the build of the material? So you can alternate powder consolidation, the standard one, with providing this time a solid confining medium on top, which can be glass, for example, and then using two different lasers, one for the standard process and the other one for the laser shock pinning. In doing that, you actually control what happens not only on near the surface, but in 3D. And we have shown that in doing that, in particular, when you're close to the finishing the fabrication in the last few layers, you can actually increase the compressive zone here, that's the top surface, compared to the surface treatments. And that's what we call 3D LSP here. You can also compare with the shot pinning, which is also another way of introducing compressive stresses when you send little balls at high speed on the surface. So these are usually more considered as more efficient and therefore are better in particular for the fatigue life of the material. So this is just one illustration here on stainless steel, where you see that the 3D is a SN curve here. You see that the 3D LSP material in fatigue under bending is way better compared to the surface treatment itself by 2D LSP and the as-milled material here in blue. In that case, you have like a fatigue life which is increased by almost 15 times, and the fatigue limit which is increased by 1/3. You have also a conventional material 316L, which is even lower here because the grain size was bigger and the hardening is not the one that you get in additive manufacturing. And if you heat the material, you realize that you are even lower, again, because of the increase of the grain size and the decrease in the dislocation density. So that's the HIP one compared to the as-built one here. So that's one benefit, but I want to come back to these cracks that Stephen has been showing. Oops, maybe I need to remove. Okay, maybe I need to show it like this. So if I, oh, that's not it. Okay, I hope you see it. So again, this is the crack that Stephen showed. Right now, these micro cracks appear, and we have seen that we can actually distinguish when the laser passes, when the crack is created shortly after. In this case, is 1.5 millimeter later. If we do, if I show a second movie here, what I want to emphasize in this case is that not only we see the formation of porosities and cracks, but sometimes, so this is the formation of both, but later on, we also see the removal of them. So removing porosity here just happened, and then removing crack on top. Then we have seen it comes back afterwards. But there are ways of visualizing how these are being created and removed. I don't go into details because Stephen explained that very well. But I just want to point out these two liquation and solidification cracking mechanisms that he underlined. So if we have that in mind, actually, we can come back during the fabrication of the material. Oh, let me swap maybe here. Yes, so you can come back here and say, why? Well, we need those cracks. We know that they are being created when you have tensile stresses here combined with solute segregation, in a sense. So why not during the build apply laser shock pinning along the blue line, for example, here, but we can do that repeatedly. And in that case, you can keep adding material on top. And when you add more material, you add more heating. So then this time you have compressive stresses underneath, they are no longer tensile, and then you add heat on top. And actually what we have shown in such a case is that, well, if you're close to the zone where you had more heat, then you actually are able to completely metallurgically heal the cracks by combination again with the compressive stresses. If you go a little bit away from, in this zone here, for example, away from the top surface, then the heat is not so high anymore. Then you have semi-healed cracks. And if you go further away, then you have closed cracks, but they are not healed because of the lack of heat. So you could imagine that you do that repeatedly, and we have done it only once here, and that you then, we have shown that it can reduce the crack density up to 90 or 95%. So the idea is, again, you suppress these tensile stresses, you make them compressive, because here you have a local lower melting point due to the segregation that was mentioned already by Stephen. Well, you have some kind of a flash heap with the advantage that with heaping, well, you have large grain growth, sometimes recrystallization, lower dislocation density, and so on. In here is all very fast and consistent with the building of the material. So that's one illustration of the kind of healing that we could do, but there could be other ways like remelting, as I mentioned before. So I will conclude here by saying that these processing maps based on normalized enthalpy have shown to be very useful for different types of materials. And in particular, we can jump from one material to another using the translation rules, which only require to measure the powder bed absorptivity and also to know the standard material parameters of the materials. Acoustic emission is also an interesting method for monitoring defects and distinguish in particular the different types of porosities. We also want to apply that to the cracking phenomena. And then if we identify either porosity or cracks, we can try to heal them. And one way of healing cracks in a nickel-based superalloy would be to use the hybrid process, combining laser powder bed fusion with laser shock pinning. Future work, well, we will use more and more the translation rule for other materials, but also going from one machine to another, and also maybe checking what happens if you change the sample size and shape, because then the thermal effect would change. And as I said, for the monitoring, we want to go further into localizing the defects from acoustic emission and repairing. And we want to automate more and more this hybrid process that I presented. Thank you. I'm done with the presentation. I will be happy to take questions.
Thank you, Roland. Thank you very much. So the floor is open for questions. Oh, do we already have two? No. Okay. Aude, yes, please. Aude, yeah.
If maybe someone was before me, no?
No, I think someone clapped. So Roland, you had claps.
I don't see the...
I got to. Thank you, Roland. That was really exciting work. Really nice. I really enjoyed the laser shock peening stuff. I wasn't aware of that. So I was just wondering about the mechanism of healing. I think you kind of mentioned that you have partial melting. Is that what is happening when you have this healing of the crack after closing it? Yes,
indeed. So it's reversing somehow. We discussed before the equation cracking mechanism, where basically locally the temperature is not high enough to melt completely, but only melting at the region where you have segregation, which lowers the melting point, right, near the crack. Now, that means if you have a crack there, you know that there is a segregation that lowers the melting point. So you can actually reverse somehow the cracking mechanism by heating again in the same temperature range, not melting, because the melting is done on the upper layers where you do the powder bed fusion, but it's high enough that this probably again comes as a liquid film here, but instead of having tensile stress here, you have compressive stress, and that's then how you weld somehow the crack which had been created.
So the segregation is helping.
Yes, in a sense that otherwise you would, if you don't locally melt, probably you would need much more time here because it's liquid. You can melt very quickly. Yeah.
Very nice. Thank you.
Eric? Eric, can you unmute yourself, please? He can't. Wait, hold on. Did I not give that permission?
Oh.
I think you have the permission.
Yes,
now
yes.
Okay.
Now I can speak.
Okay.
Thank you. Roland, thank you very much for the talk. Very interesting stuff. I was also intrigued by the 3D LSP, and I was wondering if you could share with us on a technical note how it works. Like, do you have the nanosecond laser implemented in a machine? Do you have the automated glass plate? Like, how many glass plates break when you press them on your uneven bed and stuff like that?
Yeah, well, that's you're right to. If you see what we would like, my last attempt here was to have something much better automated. At this point, it's still very, I would say, manpower demanding, in the sense that what we published so far, we take the material out, we apply laser shock peening, and we put it back. Now we have started using solid confining media, as I showed. And indeed, the issue is how much shocks they can undergo before cracking. So we are trying different solutions, combinations also of different layers, one being to absorb the shocks and the other one being really to confine the shock waves. So it's not completely automated at this point. We keep working on it, but it's not at the stage where it's fully automated. Yeah.
Do you actually also change the surface? I mean, is it sort of flattening the surface a little bit? Is that an additional benefit, or is the actual deformation negligible?
Yeah, it does change a little bit the roughness of the material when you do it, but that's not the main advantage. I would say it depends on the initial roughness. It has many other side advantages. It does reduce the porosity size, which are below the surface if they're not too far away. That we have measured. It increases slightly, of course, the dislocation density. And because of that, when you do a heat treatment, it changes the behavior as well. For example, it may influence the recrystallization behavior afterwards. So there are many other aspects of this that we can use. Here I just illustrated the healing of cracks.
Thank you.
Thanks, Eric. Elena? Elena, I see that you have unmuted, but we can't hear you. Sorry, we still can't hear you. You can't hear me? Okay. Maybe can you try turning on your video?
Or on the chat, maybe.
The chat, ask the question on the chat.
Yeah. Maybe in the meantime, I can ask a question. Roland, do you have the possibility to heat your powder bed and see if this can help the process of crack healing?
Yes, we can do that. We have a limited heating capability in the in-house machine, but we can go up to, I would say, 100 or 200 degrees.
It should be sufficient, no?
Well, actually, if you realize here the temperature that you need to reach, if you remember the simulations from Stephen, you need to reach much higher temperature to be able to locally melt. Here you need to be higher than 800 degrees. So actually, yeah, you would start from 200 instead of room temperature, but also it's usually at the bottom, and it depends on how high you are in the building, how effective the heating would be in your sample. But it's still, the major part of the heating comes from really the heat supplied by the laser for the additional layers that you build on top. That's the trick, actually.
Yeah. So Elena's question is, how does the LSP affect the microstructure of the sample?
So it's a small amount of plastic deformation that you introduce, which is enough to change the residual stresses significantly, but then it hardens the material. So as I said, you increase the dislocation density of the material, and you can actually quantify that by doing micro hardness measurements locally. That is now, if you talk about, as I said, also porosities, if you consider that they are part of the microstructure, they are being reduced as well. Now, if you have a larger dislocation density, that means also if you do a subsequent heat treatment, it's going to change the behavior. But other than that, because it's small amount of deformation, of plastic deformation, you don't have, like, for example, the grain shapes don't change that much and things like that. The texture doesn't change that much either.
Okay, maybe we can take one last question from Saad Ahmed. It's in the chat. How effective is the acoustic emission technique compared to the X-ray CT technique in terms of defect monitoring?
Well, first of all, this is meant to be during fabrication itself, where CT is done afterwards. So that's a major difference. Second thing is that it's fast. So you can actually record the signals and analyze them quite quickly compared to the measuring of a CT scan. Now, of course, in terms of localizing the defects, at the moment, the CT is really good, very precise, and we're still working. For the moment, we have an acoustic signal, which is kind of an average of on a one-line scan. We can reduce the size of the line scan, but we don't have at the moment, but we're working on it, but a precise location of the, so that means it's easy. You put a microphone in a machine, and that's it. You record it. So it's very compatible with implementation in a commercial system or a widespread use. Of course, then you need some advanced algorithm to analyze the results based on machine learning, as I showed. So that's an additional burden, I would say. So it has the advantage of being very flexible and fast, but it requires a lot of post-processing, I would say. Okay,
thank you, Roland. Maybe, okay, one very last question and then we stop this session. Pushkar, please.
Yeah, can you hear me now?
Yeah.
Yeah, thanks for the presentation. It was interesting, but I have one question just out of curiosity. So in laser shock pinning, a nanosecond pulse laser was used, and I believe you also need a transparent layer to compress the shock wave that indeed generates the compressive stresses. But I have read in one paper that with femtosecond laser, you can also do a shock pinning treatment in air. So do you think it's a viable alternative for nanosecond pulse laser?
Okay, the sound was not very good, so I hope I understood the question. So the question is whether instead of using nanosecond lasers, whether we could go up to femtosecond lasers to create the shock wave. Yeah. So yes, there are some indications that these even faster lasers could be used. Now the question is also, what is the size of the beam and what is the penetration depth of the effect that we are looking for? If you have the size of the beam which is too small, then the shock wave propagates in 3D instead of 2D, and so you lose actually in terms of penetration depth. So that's why we like usually to have typically a millimeter size beam size, such that it penetrates up to 1 millimeter, as I said. Now, if you use those ones, you could, it's just more expensive in terms of processing time, because instead of doing that every 10 layers, for example, you would do that every single layer. So, but it's a possibility, yeah.
Okay, thanks.
Okay, thank you very much, Roland. And thanks to all the speakers for this morning session. It was very nice. And just to let you know, we have a second session commencing at 1:30 p.m. So just after lunch, please join us again. See you then. Have a good lunch, everyone.
Thank you.
Thanks, Manas.